In this video, we will solve 3 applications about photoelectric effect. Let us solve application 1 together. A cesium plate of threshold wavelength lambda 0 equals 0.59 micrometer is illuminated by monochromatic radiation whose wavelength is lambda equals 0.7 micrometer. Given the speed of light in vacuum 3 times 10 to the power 8 meter per second, Planck's constant h 6.6 times 10 to the power minus 34 joules times second, and the mass of the electron Me equal 9.1 times 10 to the power minus 31 kilogram. Part 1. No emission of photoelectrons from cesium plate. Why? The wavelength of the radiation is greater than the threshold wavelength. So lambda equals 0.7 micrometer greater than lambda 0, which is 0.59 micrometer. And since the threshold wavelength is the maximum which is capable of extracting electrons from the surface of this metal, thus lambda equals 0.7 micrometer is incapable to extract electrons from the surface of cesium. Part 2. Calculate the energy of each incident photon and the work function of cesium. Is the result compatible with the answer of part 1? The energy of the photon equal to h nu, where h is the Planck's constant and the nu is the frequency of the photon. We then can write E photon equal to hc over lambda. Instead of nu, we wrote c over lambda. C the speed of light in vacuum and lambda is the wavelength of the photon. Then we can plug the numbers. Instead of Planck's constant h, 6.6 times 10 to the power minus 34 times 3 times 10 to the power 8 instead of c over 0.7 times 10 to the power minus 6, which is the lambda. And the answer is 28.3 times 10 to the power minus 20, or scientific notation 2.83 times 10 to the power minus 19 joules. This is the energy of one photon. The work function is h nu 0. And also we can write it h times c over lambda 0. Lambda 0 is the threshold wavelength. Then we plug the numbers, 6.6 times 10 to the power minus 34 times 3 times 10 to the power 8 over 0.59 times 10 to the power minus 6. And the answer is 33.6 times 10 to the power minus 20, or scientific notation 3.36 times 10 to the power minus 19 joules. We can conclude by comparing the energy of the photon and the work function, where work function is greater than the E photon, 3.36 greater than 2.83. Then no emission of photoelectrons. This result is compatible with the answer of part 1. Part 3. The cesium plate is illuminated by another electromagnetic radiation of wavelength lambda prime. Electrons are ejected with maximum speed, V equal 5 times 10 to the power 6 meter per second. Determine the value of lambda prime. We will use Einstein relation. Kinetic energy maximum equal to the energy of photon minus W0. So kinetic energy max equal h nu minus W0. W0 we already calculated it. So half m v square equal to hc over lambda prime minus W0. We can plug the numbers. Half times 9.1 times 10 to the power minus 31 times 5 times 10 to the power 6 all square equal to 6.6 times 10 to the power minus 34 times 3 times 10 to the power 8 over lambda prime minus 3.36 times 10 to the power minus 19. The answer before the equal is 113.75 times 10 to the power minus 19. And h times c is 19.8 times 10 to the power minus 26 over lambda prime minus 3.36 times 10 to the power minus 19. We can take this value before the equal, it will be positive, and the answer will be 117.11 times 10 to the power minus 19 equal 19.8 times 10 to the power minus 26 over lambda prime. And thus lambda prime is 19.8 times 10 to the power minus 26 over 117.11 times 10 to the power minus 19, which is equal to 16.9 times 10 to the power minus 9 meter. Instead of 10 to the power minus 9, we can put nano. Then it is 16.9 nanometer. Now second application. Application 3. Given Planck's constant 6.62 times 10 to the power minus 34 joules times second, and 1 electron volt is 1.6 times 10 to the power minus 19, the elementary charge E 1.6 times 10 to the power minus 19 coulomb, and electric charge is Q equal Ne, where N is the number of electrons. Mass of electron is 9.1 times 10 to the power minus 31 kilogram. A photocell is a device which converts radiant energy into electric energy. Figure below is a simple diagram of the circuit of a photoelectric cell, which includes a dry cell, a galvanometer G, a cathode, which is a pure metal, and anode. We consider two photocells of cesium and magnesium cathodes, whose work functions are 2.1 electron volt and 3.7 electron volt respectively. Part 1. We illuminate each of the above cells by a radiation of wavelength lambda 0.55 micrometer in vacuum. Part A. Electrons are not liberated from the surface of magnesium. Justify. So E photon equal h nu. Instead of nu, we can write C over lambda. Then the energy of the photon equal 6.62 times 10 to the power minus 34 times 3 times 10 to the power 8 over 0.55 times 10 to the power minus 6. And the answer is 36.1 times 10 to the power minus 20, and as scientific notation 3.61 times 10 to the power minus 19 joules. We can convert the joules into electron volt to compare it with the work function given. So the energy of the photon is 3.61 times 10 to the power minus 19 over 1.6 times 10 to the power minus 19 equal 2.26 electron volt. Now we can compare it with the work function. The work function is 3.7, which is greater than the energy of the photon, then no emission of photoelectrons from the surface of magnesium. Part B. The total energy of two photons of the incident radiation is greater than the work function of magnesium, even though no electrons are emitted from the surface of magnesium. Justify. In photoelectric effect, each effective photon interacts only with one electron, one-to-one interaction. The electron cannot absorb the energy of two photons. Part 2a. Determine the maximum wavelength lambda 0 of a radiation capable of liberating electrons from the surface of cesium. Is this radiation visible? Why? The work function is h nu 0. Nu 0 is the threshold frequency. Instead of it, we can write C over lambda 0, where lambda 0 is the threshold wavelength. And thus lambda 0 equal to h times C over W0. We can plug the numbers. 6.62 times 10 to the power minus 34 times 3 times 10 to the power 8 over 2.1. This is electron volt. We should convert it into joules. And we know that each 1 electron volt equal to 1.6 times 10 to the power minus 19 joules. And the answer is 0.59 times 10 to the power minus 6 meter, which is 590 times 10 to the power minus 9 meter. And instead of 10 to the power minus 9, we can write nano. Then it is 590 nanometer. 500 nanometer is a visible radiation since it is within the visible range. 400 nanometer to 800 nanometer is our visible range, or 4 micrometer to 8 micrometer. The 400 nanometer is the violet color and 800 nanometer is the red color. More than 800 it will be the infrared, and less than 400 it will be the ultraviolet. Part B. Determine the maximum speed of the electron liberated from the surface of cesium when illuminated by radiation lambda equals 0.55 micrometer. We will use Einstein relation, the kinetic energy maximum equal to the energy of photon minus W0, work function. Kinetic max equal h nu minus W0, then half mv square equal to 2.26 electron volt minus 2.1 electron volt equals 0.16 electron volt. Now we can convert electron volt into joules. 0.16 times 1.6 times 10 to the power minus 19 joules equal to 2.56 times 10 to the power minus 20 joules. And the velocity will be equal square root of 2 into 2.56 times 10 to the power minus 20 joules over the mass of the electron, which is 9.1 times 10 to the power minus 31 kilogram. Then the answer will be 2.37 times 10 to the power 5 meter per second. This is the maximum speed of the electron. Part C. The radiation of lambda 0.55 micrometer is incident on the cesium cathode. The anode is connected to the positive pole of the dry cell, so it is positively charged. Suppose that all the liberated electrons are attracted by the anode and transferred to the positive pole of the dry cell, thus forming a current I equal 40 microamp. Part I, determine the number of electrons liberated from the surface of cesium during 1 second. Hint, use Q equal I times T. So the charge equal to N times E, and also Q equal to IT. So now N equal I times T over E. The current is 40 micro times the time 1 second over 1.6 times 10 to the power minus 19 the elementary charge. And the answer is 2.5 times 10 to the power 14 electrons. Of course, we call these electrons photoelectrons. Part 2i. For this radiation, the quantum efficiency of the cell is 3%. Deduce the power of the radiation received by cesium cathode. The number of electrons emitted is 2.5 times 10 to the power 14 electrons, which is the number of effective photons. So quantum efficiency is R equal N effective over N total. Thus N total equal N effective over R. The N effective is 2.5 times 10 to the power 14 over the quantum efficiency is 0.03. 3% we divide it by 100. Thus the total photons in the incident radiation is 8.33 times 10 to the power 15 photons. The total energy received by the cathode is the energy of one photon times the number of the photons. So N total times E photon. N total is 8.33 times 10 to the power 15 times 3.61 times 10 to the power minus 19 joules is the energy of one photon, equal to 3 times 10 to the power minus 3 joules. So the total power is E total over time, 3 times 10 to the power minus 3 over 1 second equal 3 times 10 to the power minus 3 watt. 3i. Specify how should we modify the following factors: the power, the exposure time t, the frequency nu of the received radiation in order to increase the kinetic energy of the liberated electrons. To know what we should do here, let us use Einstein relation. E photon equal W0 plus kinetic energy max. So H nu equal to W0 plus kinetic energy max. W0 is the work function, so it's constant for each metal. Thus, to increase the kinetic energy of photoelectrons, we should replace the incident radiation by another one of higher frequency. No effect for the power and time exposure on the kinetic energy. Part 2. Increase the number of liberated electrons. To increase the liberated photoelectrons, we should increase N effective, since N effective equal to the number of photoelectrons. And to increase N effective, we should increase the total N. P total equal E total over time, thus P total equal N total E photon over time. So N total equal P total times T over E photon. To increase N total, we should increase the power of the incident radiation or increase the time of exposure. The third application, application 4. A surface of a metal of work function W0 emits electrons of maximum kinetic energy Ke. When illuminated by a radiation of frequency nu, the graph represents the square of the maximum speed v of liberated electrons as function of the frequency nu of the incident radiation. Given 1 electron volt equal 1.6 times 10 to the power minus 19 joules, Planck's constant 6.6 times 10 to the power minus 34 joules times second. Part 1. Determine the expression of V square in terms of h, W0, nu and the mass of electron. Deduce the form of the curve that represents V square as function of nu. Einstein relation E photon equal W0 plus kinetic energy max. Then h nu equal W0 plus kinetic energy max, or h nu equal W0 plus half mv square. Let us rearrange the equation. V square equal 2h nu over mass minus 2w0 over mass. The equation is of the form V square equal a nu plus b, which is a straight line equation. Of course, a is 2h over mass and b is minus 2w0 over m. Part 2. Determine the equation of the curve in the graph. This is the given graph, V square in terms of nu. We can observe that the curve is a straight line that has a constant slope. Thus our slope is delta V square over delta nu. We will take 2 points, these 2 red points. Then the slope is 1 times 10 to the power 12 minus 0 over 14.5 minus 7.6 times 10 to the power 14. Take care that 10 to the power 14 and 10 to the power 12 are given here beside the units. So the answer is 1.45 times 10 to the power minus 3 meters squared over second. And since the graph is a straight line, we can write the equation as v squared equal a nu plus b. A is the slope, 1.45 times 10 to the power minus 3 nu plus b. We can substitute the coordinate of one point to calculate b. So for nu is 7.6 times 10 to the power 14, v squared is 0. Thus 0 equal 1.45 times 10 to the power minus 3 times 7.6 times 10 to the power 14 plus b. So b equal minus 1.102 times 10 to the power 12 meters squared per second squared. And thus the equation becomes v squared equal 1.45 times 10 to the power minus 3 nu minus 1.102 times 10 to the power 12 meters squared per second squared. Thus this is the equation of the graph representing v squared versus nu. Part 3. Determine the mass of electron. We have the relation v squared equal 2h nu over mass minus 2w0 over mass. And we already calculate the equation of the graph v squared equal 1.45 times 10 to the power minus 3 nu minus 1.102 times 10 to the power 12. So by comparing the two equations, the slope is 2h over mass, which is equal to 1.45 times 10 to the power minus 3. So the mass equal 2h over a, 2 times 6.6 times 10 to the power minus 34 blanks constant over 1.45 times 10 to the power minus 3 the slope. And the answer is 9.1 times 10 to the power minus 31 kilogram. Last part 4. Deduce the value of the work function in electron volt of this metal. Again, the relation we have v squared equal 2h nu over mass minus 2w0 over mass. And the equation of the graph, already we know it. And by comparing the two equations, B equal 2W0 over mass, which is equal to 1.102 times 10 to the power 12. Thus W0 equal B times M over 2, 1.102 times 10 to the power 12 times 9.1 times 10 to the power minus 31 over 2, and our work function is 5.014 times 10 to the power minus 19 joules. To calculate it in electron volt, we should divide by 1.6 times 10 to the power minus 19. Thus the answer is 3.13 electron volt, and this is the work function of this metal.